guess it's better to be in the main building than over on the annex across the walkway, lost in the ZOS people. Well, I know. At least I got one seated question. I know somewhere in here. Sure.
It's a minute early, but we can get started. So I'll get us downstairs a minute
Yeah,
as well.
exactly 1 minute early.
So thank you all for coming to the virtually constrained or really overcommitted presentation that Adrian Burke is going to give. He's from the DB2 SWAT team from the California DB2 lab, Silicon Valley. So if you've probably heard this before, but if you have put your cell phones on not loud, vibrate or silent, please. And with that, we'll get started with Adrian.
Thanks. As long as it's not that annoying Samsung ring, we'll be okay. Kill me. Afternoon. Okay, so I'm the last thing between you and happy hour, so we'll get this done on time. My name's Adrian Burke, as you mentioned. So the SWAT team is the customer-facing arm of the DB2 development lab. So John Campbell is my team lead. I'm the only one in the Western Hemisphere. I'm the only one without a cool British accent, but I am also the only one that's sniper qualified on the team. So the only thing that SWAT applies to actually is me. So that's where I go with this. So this topic, when we go around the world, we do these 360 studies. We call them, they're kind of performance as well as availability studies. And from that, we glean a lot of insights about what customers are doing these days, what they're doing well, and what they're doing not so well. So that's where a lot of this comes from. I was hoping with the advent of the Z13 and a much diminished storage cost for central storage on there that we wouldn't have to talk about this anymore. But apparently we do, because it's in at least 2 or 3 sessions here at Share this year. So quick agenda, go through storage terms and concepts, then really get into what you care about from the DB2 side relative to the ZOS side, how real and auxiliary storage affects us, and what to do to fix it, hopefully. I've got to have pictures in here. So at most of the customer sites we go to, they think that everything they have is in central storage, or if it's out in auxiliary storage, it's not a big deal. And I use this example because I spend a lot of time on planes and a lot of time to get here on planes. I think when I came through Philadelphia, we were number 22 on the tarmac in line for takeoff. So lots of good time in the seat back there. But what we actually see when we go pull the customer data out, right, IFCA 225 or some of the SMF data, what we find out is that some of their most prized possessions are out in auxiliary storage, right, somewhere in DASD. By the way, if this were American Airlines, you would have had to pay $500 for the kid's actual seat and another $150 to put them in the overhead bin, right? So don't do this. Okay, kicking off. Real quick, gonna blow through kind of the basic concept stuff to set the stage. So what's virtual storage, right? It's ZOS tricking you, right? It's its way to be able to address more than you can actually hold in central storage. Right? Virtual storage came about back in the, really for MBS XA, right? Where you could have 2 gig of storage in virtual storage, but you only had, what, between 8 and 64 meg in the box. So that's the point. When I talk about real storage, I'm talking about what you paid for on the KEK, in the drawer, in the box, in the refrigerator looking thing, right? Auxiliary storage is how much you have in your page data sets out in the DASD box. Executing pieces of the program obviously are in real. If we're gonna update data or change anything, it must be in real. Once we've finished it, then we can write it out to storage or an auxiliary. When we address it, or when ZOS Real Storage Manager addresses it, it's going to do it in chunks. So we got 2 to 8 gig region sizes, then we go down to the 1 meg segments, and then the 4K page. If you look at this 1 meg segment, ironically now we have 1 meg frames in real storage, right? So we'll come back to this concept a little later. We use dynamic address translation, and this can be improved and save CPU cycles if we use larger frames. We'll talk about that a little bit earlier. We're talking about the different sizes. In virtual, you've got 4, 8, 16, 32. Think of your buffer pool sizes, as well as 1 and 2 gig. We're talking about real. I've just got the 4, 1 meg, 2 gig as far as the frames. And if we're talking about things out on auxiliary, everything's kind of based on a 4K sizing. So I'm looking at the map. We're going to talk about real storage. I'm talking about a frame. Virtual storage, talk about a page. Auxiliary, I'm going to say slot. And if you have storage class memory, it's called a block now. That's Flash Express. Does anybody have Flash Express storage on the box or where? A couple folks, okay. So I'll beat this topic up later, but basically it's auxiliary storage that you put actually inside the KEK, right? So it's like a thumb drive, so to speak, for your mainframe. Don't plan on putting your buffer pools there, right? But it's a good little insurance policy. Okay, how do we get through the available frame queue? So ZOS manages this, right? He does it on an LRU basis, just like you would for a buffer pool. When he gets low, he's going to start paging. The thing that we commonly find that storage capacity planners or capacity planners in general have a problem with is using the unreferenced interval count, the UIC, as far as looking at how much available storage they have. That is actually the useless interval count, the UIC. Most of the customers I go to see that they have 18 hours, right? So the highest that can be, the UIC, is 65,000. And they say, oh, look, everything's been in storage for 18 hours while DB2 is paging like mad out to aux, right? The problem is the UIC looks at the last time every single frame in the box was referenced. Well, you may have a large LF area defined, or for instance, page fixed buffer pools that nobody else can reference. So you've actually stored them away, and that count will never increase. So don't use this as far as keeping track of whether or not you're paging or how comfortable you are on storage. The Makafka, I'm not sure who named this, but ZOS has even worse naming conventions than DB2 does. But this basically controls at what point you page. So you get down to 0.2%. If I got 100 gig LPAR at 200 meg, I may start paging. If you've got a huge LPAR, this thing can be changed dynamically in the background without you messing with it. If you've got enormous LPAR, he's not going to page when you still have 60 gig left on the box. But this is kind of interesting to understand when it kicks off. It's not absolute zero. So in ZOS, and I realized this just a couple years ago, it's important to understand what it's going to do in reaction to you over-allocating storage for DB2, for instance. So if I got too much fixed storage on the box, not enough free, not enough storage open for other people to use, at 50% of the box, so say you're playing with page fixing buffer pools, you got a 100 gig box, you page fix 50 gig and DB2 comes up and allocates it. Well, we're going to get an informational message out, an event notification, 55. If you get up to 80% in real, it's going to throw out the IRA 400 messages, and it's going to tell you the top 20 consumers. And it'll take the biggest consumer, if it can't fix this storage issue, and it will make him non-dispatchable. Does everybody know what that means? He gets no love, right? He's basically frozen in time on the LPAR. So if you really want to screw up a box, freeze or make non-dispatchable the largest consumer of storage, right? So he can't process and get out of the way, like a sort, for instance. If you get up to the critical storage at 90% of this, then the stuff is already non-dispatchable. We're going to stick a message out for those top 20, and we're going to allow you or the operator to cancel them, to kill them, right? And that will not come down pretty as far as when that address space ends. Why do I put this in? Because, of course, I've seen it happen at a customer. So this customer deals in healthcare, and I was actually on site when this happened. They page fixed their buffer pools, and they used a super cool new feature in version 10 called auto size, right? So auto size is WLM telling us, hey, your buffer pool is kind of small. We're waiting on sync IO delay. And if you start to approach your WLM service class, he'll start increasing the buffer pool or decreasing. But usually he just likes to make it bigger, right? So he'll increase it up to 25% of its initiating size. Well, every time you bounce DB2, it has amnesia, and it gets another 25% that it can allocate. So eventually it'll keep growing. This customer, there's multiple DB2s and obviously multiple buffer pools on this LPAR. They bounced it a couple times. They were kind of short. They're also short on real storage. So on a 25 gig LPAR, the buffer pools cumulatively came up and took over 20 gig. And at this point, DB2 became non-dispatchable because he's the biggest one in the box, right? So at 10 a.m. on Monday, the LPAR ground to a halt, and they had to bounce DB2 to get rid of it. Where they had to bounce DB2, alter the buffer pools, page fix no, and then bring it back up again. So watch out for that one. Fine if you want to do it in a test LPAR, but be careful with auto size. And in 11, at least, you can say the min and max, so it won't run away on you. Auxiliary storage, right? Talking about the storage in your page data sets out on DASD. This one is even more important. When you use 50% of this, we send another event notification, and DB2 listens to this, and you will see master address space burn like you've never seen it before if you end up using 50% of auxiliary storage. At 70%, once again, we'll mark some of the largest consumers non-dispatchable. If you look in the DB2 listserv, you'll see indications in here where you get negative 904s for instance, dynamic statement cache. Strange things where you can't get access to storage, and that's where we're going to have to somehow free up what's out in the page data sets. The answer to solving most of this is to put it or have a larger central storage repository, right? And if you get up to 85%, same thing, we'll give you the top 20 consumers. If we can't fix them or go away, you can cancel them. What happens if you hit 100% on aux? Anybody? Think horrible. The LPAR comes down. Woo! Right? And you get a free IPL in the middle of the week. Okay. Didn't even have to schedule it. So next step, looking at real storage. I'm going to build this up because we've had an APAR that came out and it went hyper. So it's kind of an interesting case here. In the storage set up by ZOS, you've got pieces that you can control, for instance, to 2 gig and 1 meg. So these are large frame areas, right? In version 11, you can have buffer pools backed by 2 gig frames in real. So that saves some CPU because instead of having to go through the 255,000 whatever 4K frames, we map it into one big 2 gig. So we save in the dynamic address translation. You set these guys up. Usually it's the capacity planning people, and they either far under or far oversize it. But these are up to you. These pieces are all controlled by ZOS. And up until, I don't know, early last year, nobody bothered calculating it. But now we at the lab are interested. So quad area, large pageables, and this area down here, ZOS reserves, right? And this one in particular, the quad area, is 1/8. So just as soon as the ZOS comes up, he takes 1/8 of the LPAR and reserves it for this, and another 1/8 for pageable. Well, we had a customer that ended up with, say, 45 gig of free storage on the LPAR, but DB2 was paging like mad. So every day, there'd be another couple hundred meg of DB2 in an aux storage, even though there was 46 gig free on the LPAR. So they didn't understand why this happened. Problem was, ZOS wasn't breaking down the quad area. So he reserved 1/8 of it and wasn't giving it back for anybody to use. So now we're going to customers and trying to convince them to use this very simple mathematical process to figure out whether or not they're kind of living on the edge. So if I've got 100 gig LPAR and I convince my capacity folks that I could use another 100 gig more for buffer pool and make DB2 run much better, he gives me 100 gig. Well, I page fix the buffer pools and I assign LF area, or the large frame area, to house this 100 gig that I added to the buffer pool. So now I'm going to get CPU savings from page fix and from large frame. The problem is, in the background, ZOS is reserving 26.5% of the LPAR for himself in case he needs it. And he doesn't like to break these areas down unless he really has to. So you'll probably end up paging before we break this down. Well, in this case, before he added the storage, he got 73 gig of free. That's for left around for 4K for other address spaces and stuff to use. Now, in this case, I quarantined my 100 gig. We do the same math, and lo and behold, we've actually got 40% less storage for everybody else to use. So if you're using 50 gig on the LPAR, in this case, now you're paging. How'd I add 100 gig of storage and now I'm paging, right? So this is the kind of math that you have to go through. If you're going to start allocating LF area and other things, you need to understand what's left, right, for everybody else to play with. You should ask, who's using page fix buffer pools? A couple folks, all right. And large frame area? Same thing? Okay. So this one, this is a ZPARM that we put out in version 10, Real Storage Management. Most people probably aren't aware of it, but it's become a hot topic in level 2 PMRs recently. So I'm trying to dispel some myths or maybe give you some nuggets to take home. So this is kind of a verbose slide. What it says is this ZPARM is for DB2 to be a good corporate citizen and relieve some of the thread storage after the thread deallocates or so many commits. It's us taking our 64-bit shared storage that we're using for threads and giving it back. Because if you look on your storage mapping, DB2 looks like it uses a lot in high shared, right? Because ZOS can't accurately count how many frames we're using, so we look overinflated on the chart. So there's 3 settings for this, on, auto, and off. Auto is there by default. That's what you get, which means after 120 commits or deallocate, we give the storage back to ZOS. We have another, so that's called discard mode, right? When we discard the frames back to ZOS. We have something called hard discard, which means we not only give the page back to ZOS, but we erase our name off of it so he didn't know that we ever used it, right? And that is a more accurate way to present storage to ZOS. We'll only hit this, which burns a lot of master address space, if 50% of aux is used. Then we go into this discard mode, or you've hit another ZPARM, Real Storage Max, which you should not have set in the first place. So you want to automate on this message, the DSNV mons. If you have 516 or 517 in there, you're already short on aux, right? And DB2 is getting the message and trying to go through and free off storage. So if you see strange CPU burns in certain intervals in the master address space, it could be it. So now when customers, for instance, move to a new release or have some big application upgrade and they see address space burn in DB2, one of the things that unfortunately we started looking to is this RSM ZPARM. So here's an example of when it was effective to use. So if you have ample storage on the LPAR, you did the math from a couple slides ago and you're good to go, turning this off could save CPU, could save master address space, SRB time, as well as dist and maybe even DBM1. It also saves basically what you would call the non-accounted for time as far as ZOS, the uncaptured time. So this is an example. I went to a customer site. They saw a huge DB2 burn. At some point, it was taking 2 processors just for the address space itself. The problem was the IMS region, which I'm showing up here, was thrashing like mad. So when IMS had trouble, they lost all thread reuse in DB2. So every single tran that went through burned 20% more CPU than it did with thread reuse. So this is the threads deallocating. They're usually creating about 50 to 100 threads a second. During the burn, they're creating 450 threads a second. And what I'm showing down here is that the master SRB time is using half an engine by itself. DB2 is using 1. I said, well, until you figure out what the problem is with IMS, you can turn this PARM off temporarily and alleviate the burn in master. So they turned it off, and we saw a 4x reduction in master SRB time. If you do this, if you have good thread reuse all the time, this PARM will do almost nothing. But the downside of turning it off is you'll see growth in a high virtual shared. So HV share, 64-bit that DB2 is using, is going to grow some, so you'd have to monitor it. But this is kind of a little trick we have in our bag for saving master CPU. Has anybody played with that parameter? You can go home and try it, but don't tell anybody who you heard from. Okay. This is the audience participation, so what's a tolerable paging rate for DB2? Perfect. Good. We got the Jesus answer. Okay. We finally got Poughkeepsie actually to measure it too. So now they've admitted that it costs 20 to 70 mics, right, per I/O. So you're going to pay that for the I/O you intended, right, coming in from DASD because it wouldn't fit in the buffer pool, or you'll pay it almost double if it's paging, right? So if you were short on central storage and we paged it out to aux, it's the same cost to bring it in for an I/O there as well. And don't forget you got the actual elapsed time. What I've seen at several customers is they've vastly undersized their test dev environment, right? So I had a large customer in the south that's very penny pinching, we'll say, and I said, why are you paging so much in test dev? Add a couple more gig to that thing and just keep it in storage. Like, well, storage costs money. Well, I did a little paper and pencil trick and showed that they were burning about 8 MIPS per second. 8 MIPS per second, just paging in and out of development and test. And this customer claimed that their MIPS cost them about $1,200 a piece, so that added up a lot in their MLC bill at the end of the month. So don't forget to look at those guys when you're sizing it. This is the positive view. If you have enough central storage, you can improve performance via all these methods. And I think Mark Rader is probably going to talk about this more later in the week in his. But summary to say, you can make the global dynamic statement cache much larger. SAP proved by, I think they quintupled their local statement cache, got a 25% throughput improvement on that, right? So all these things, with larger memory, come CPU savings. That's the trade-off. Version 12, we're going to continue to use more storage, right? To get more CPU savings, we're going to burn more storage. And actually, just moving to 12, the average thread footprint's probably going to increase 20%. We haven't seen this since version 10, right? When you went from version 9 to 10 or 8 to 10, we went to 64-bit. Everything got fat above the bar because it got lazy. They're going to see about the same thing with version 12. So about 20% plus or minus at the thread footprint. Now, what if you want to take advantage of CPU savings? Well, the cool thing, fast reversal block that I know my teammates have talked about in webcasts and so on, saw 45% CPU or 45% get page reduction, which is 10 or 15% CPU. To enable this, though, we may increase the size of your buffer pools by 20%. So if you're looking at your overall DB2 picture and you've got 100 gig in buffer pool, going to 120 gig is going to be noticeable, right? So when you enable this feature, you're going to use a lot more storage for that. The other one, contiguous buffer pools. Once again, we saw an 8% CPU savings. This is when we bring the object into the buffer pool, you've specified page steal none. So assuming you've already got a very specialized buffer pool, if it's page steal none, we'll load the pages in contiguously. So now we've removed all LRU mechanisms and all latch classes associated with those, right? Like 14 and 24. So that is good stuff. And no, I'm not going to update Windows. I like it where it is. I'm on a safe island of stability on my current function mode. So that's like another good CPU savings, but that means basically any buffer pool using that needs another 6,400 buffers to accomplish that. Oh, I knew I was going to do this. It's taking an interrupt now for this. Okay. Okay, here's some more horror stories, right? Everybody came to this, right, to be beaten down before you get a beer at the bar. So storage, what if you're short? We use these metrics all the time in our team. It's out of SMF 100. It's stat class 1, written at 1 minute intervals, and we use a MEMU2 Rex exec to pull it out, and then we graph it. So in this example, purple is real storage on the LPAR. It went to 0. Auxiliary storage that DB2 is using, right, out in page data sets went up by about 700 meg, and we can see the in use by DB2 went down. So DB2 is a victim. He got paged out. A little example, if it takes me 2 milliseconds per I/O for this, I'm now wasting 6 minutes bringing my DB2 back in, right, to the scrum. If you took an SVC dump here, it would be horrible, right? I told this story yesterday. I was at a customer who left a slip trap in over the weekend. Nothing happened Sunday. Monday morning, the slip trap was still there, right? And between 10 and 11 a.m., their only production system, non-data sharing, took an SVC dump and paged everybody in the LPAR out to aux. So their 4-minute dump took 45 minutes to recover from.
We had a trace going this last year. It was just sucking all the memory and CPU, and PDF wouldn't start anymore because it ran out of CPU.
So the comment is that there are traces that are incredibly CPU incumbent on that, right? And we see a lot of stuff with logging, especially. If people think they're doing tracing against log records or how often you're doing IOs, that's a lot of overhead. So in this customer example, we paged out, right? Ran out of storage on the LPAR, DB2 got paged out. Then I get a phone call from a different customer that says, my storage people are complaining that DB2 is using up all of the aux storage. Well, DB2 can't page himself out. Somebody else paged him out, right? That's kind of like blaming the prison population for overcrowding. If you let them out, they will gladly leave, right? So it's the same thing with DB2. They didn't put themselves there, nor can we put ourselves in an aux storage. So in this example, I've got, in a 2-minute interval, I got 2 gig of DB2 out in aux. So I went back to the WLM records during the same time, and I can see in the activity report the number of storage frames that this address space is using. This guy, who's in red, went from nothing to suddenly 60,000 frames in the matter of a couple minutes and then disappeared again. That's when DB2 paged out. So we found out that this, in the batch service class, was a utility, right? So that guy, for some reason, ran at 10:30 in the morning, which is a really poor time to do a utility that takes up several gig on your LPAR. So the answer to that was reschedule it, right? So there's pretty good ways to go through, but the key to getting down to the root of the problem is to find out who took all the storage and who paged who out, right? Generally speaking, a utility is an easy target, or the first one we guess about. So how do we control that? Well, aside from not scheduling it at the wrong times, there's ways you can control things like, for instance, DF sort. The key one I'll talk about here is EXP old. That's the percentage of storage you allow him to steal from the rest of the LPAR. Old means on the LRU chain, so it's older frames, but somebody may still need to reference it. So if he steals that, their storage gets paged out to aux, right? And by default, I think, at least up until 2.1, this was like 50%. So he can page 50% of the LPAR out to auxiliary for this sort to complete. If you limit it, for instance, you can also set EX Pres or EX Max to limit how much they consume. This example, the customer wanted to reserve about 5 gig on the LPAR. He set EXP Max to limit how much storage sort can use, right? This same thing would apply to sync sort, DB2 sort, and the other products, right? Just may go by a different name. Okay, continue with that vein. This customer had set that limit. He said, okay, I'm only going to allow sort or to use up to 20% of the LPAR. So EXP Max is 20%. The problem is DF sort doesn't look at the entire LPAR and get the whole picture. He came up and said, oh, there's 256 gig assigned to the LPAR. I'll take 20% of that. Well, the customer had also page fixed almost half the LPAR. So when he went to go take his 20% or 50 gig, he actually is consuming over 30% of the LPAR, right? Because he can't touch the page fixed ones, because those are all DB2 in the buffer pool. So he starts paging like mad. In this case, 15 pages a second. DB2's got a couple gig out in auxiliary storage, and that's because sort is using a lot more than they thought. So the key here would be EXP old down to 0. That way he can't steal DB2's frames. The other way you could do this, if it's a batch report, for instance, or your utility is run at a lower dispatching priority, you can set WLM storage critical for DB2, in which case that utility is not going to steal DB2 storage. He's going to go steal from Kix IMS or somebody else. The other thing that's a little confusing about auxiliary, it's also considered double accounting, right? If we use one of the slots out in the page data sets in aux, once we touch it, it's ours until the address space goes away, right? Until DB2 goes down or you recycle him. Anything we touch in aux will still be ours unless we re-reference it and bring that exact frame back in. Well, if we're talking about thread storage, it'd probably be never re-referenced, right? Because the thread went away, but it was still on the LRU chain with it. In this example, like I said, using the IFKID 225, I can track my auxiliary storage usage, and it's trending down. That means we're actually paging in those exact frames again. So this is probably a buffer pool, but pages are now being re-referenced from the same object. Usually, though, this number just climbs up and up and up and up until you bounce DB2. Ooh, buffer pools, exciting topic. Okay, so more audience participation. This is my IFKID 225 data. This is showing what's in auxiliary. These are buffer pool control blocks, and this is buffer pool storage. So I've got 1.5 gig of my buffer pool is out in my page data sets. So if I'm trying to figure this out, if I'm not pulling this data and I want to know, where am I going to see the effects? Well, I see it in sync IO. If I go to auxiliary storage, is it a sync IO or a prefetch? Well, I see it in the buffer pool hit ratio. If my entire buffer pool is paged out to auxiliary storage, could I have 100% buffer pool hit ratio? Yes. What about buffer pool residency time? If it's out in aux, it's not an IO, because Buffer Manager has referenced it once. It was in the pool last time. It should still be there. Well, if you don't have enough central storage on the box and that buffer pool lives in aux now, Buffer Manager and DB2 don't know that. We're just referencing that page in virtual. If it's really out in aux, then they're going to page it in behind the scenes. So then you get 2 IOs, or 2 IOs for the price of what you thought was 0. No. So none of those metrics will tell you if you're paging like mad. The elapsed time will go up on the application and you'll see CPU burn. Where is it? IFKID 225, the paging reports, you'll see class 2 not accounted. That's a good one if you're paging a lot. And then uncaptured in ZOS. So for some of the buffer pool people that are really tedious about their numbers, sometimes they realize that the thing's out in storage, you can actually cut the elapsed time in half of your app by add more central storage. These are the thresholds a lot of folks look for in the buffer pools. If these are hit, it means your buffer pool's too small, right? 97%, basically do a force write every time you change a row on a page. At 95%, we're going to do a get page for every single row, even if there's multiple rows on the same page. And the prefetch threshold will disable everything's a sync IO instead of bringing it in 8, 16, or 32 page chunks. Prefetch disable, though, has some interesting other reasons that we've discovered lately. One is no read engines. So you might be degraded not because of the buffer pool size, but because all 600 engines are in use by somebody else. There's only 600 per DB2. No buffer. So you've made VP sequential or VPP sequential small enough that we wanted to use these pages for sequential pages, for prefetch, and there weren't enough, so we couldn't. Another one we've discovered recently is tied back to a new feature we had in 11, which was index IO parallelism. So if you insert a row into a table and you got multiple indexes against it, we can prefetch those pages in to the pool to be updated in parallel. Otherwise, you're synchronously waiting for each index, right, serially. If you set either of these to 0, though, IO parallelism's turned off, basically, at that buffer pool level, and you'll start getting non-zero numbers for prefetch disabled. So some customers have run around in a tizzy because they thought that they were 90% dirty pages in the pool, and actually they just had this setting turned off. Page ins are very bad, right? If you're page ins for the buffer pool, for read or write, that means you don't have enough real storage. Your buffer pools might be big enough, but you don't have enough real to back it. The previous slide is your pools are too small. So here's an example of a customer that I work with, and this is funny because this is off their third-party vendor tool. At the top is their rules of thumb. If anything other than page ins is 0, increase the size of the pool. Well, he didn't put if page ins is greater than 0, then you should shrink the pool. So in this case, in a course of 5 minutes, he paged in 19,000 frames for a buffer pool that's 1,000 buffers. So he cycled through the whole thing 19 times. That application never finished, right? He's going out to the desk the entire time. Yes, Mark?
The page in for reads, that should show up on the previous slide when we said, how do you know if your buffer pools are out or not?
Okay, so
Page ins for read are right then?
So Mark's comment is if my buffer pools are paged out to aux, then this page in should be incremented when I bring it in. The only time page ins is incremented is when we get all the way back down to the oldest page in the buffer pool, the LRU, and we have to page him in. We need a frame to back that oldest page in the LRU. So this is only incremented when I'm going to steal a buffer. If I'm referencing a buffer that I referenced 2 minutes ago, it's my own buffer, then that won't increment. We'll only increment it if we're going to steal a buffer in the buffer pool for it. We can take it offline too. It's a small difference, but it's huge if page-ins could be 0 and I could be paging that buffer pool like mad. And I've seen it, and I was curious why that number was 0. Good question. First beer's on you. So the other great thing about buffer pool, if you're looking to save CPU in here, the simulation tool. Who's used the buffer pool simulation in version 11? A couple folks. Okay. It's available in CM. So awesome new feature to play with, and it's right out of the box as soon as you get to CM. So what this does, it allows you to simulate increasing the VP size or VP SEQT size and to actually see the real results of the number of IOs saved as well as elapsed time saved. And if you know the number of IOs saved, you can estimate, based on our 20 to 70 microsecond swag, how much CPU savings you could save by having buffer pools that big. Today, you either have to increase it and do your own calculation, or you can buy a vendor tool, which even IBM has, and even IBM's tool doesn't work as well as this. Why is this secret? Because we actually use the old hyperpool code in DB2. So we know exactly, if we had 10 more buffers, I would save exactly 8 IOs, for instance, because internally, we're tracking it in the control blocks. So this number is absolutely accurate for the same workload. Troy?
What I'm thinking of is that this does not take into account that you may have memory problem when you increase it that could cause you other issues. Is that
Correct. So there is, the question was, if I play with this and get overzealous and then I start paging on real, correct. This has no idea what you have left in real. This is just, if I increase a buffer pool, I'm going to save this many sync IOs for it. But it's incremental. So if I say add 20,000 buffers, it's going to add 20,000 to what I have now. And the percentage is the same thing. It's 10% of the new buffers that I add. It doesn't estimate shrinking, but as far as estimating growth, it is absolutely dead on accurate. So we've had some good strategy with this. The nice thing is this, you test it, you say I'm going to save this much, this many IOs, rough swag on CPU, and then you go back and you say, capacity people, if you give me 10 gig, I can save this many IOs, right? As opposed to having to buy it up front and then, you know, grovel at them when your estimate is wrong, right? And this is all in the code, right? It's not chargeable. It came through in version 11. So for buffer pools, I've talked about large frame area a little bit. I'll cover it in a second. And page fixing. So where do I get the CPU savings when I do these two different features? So this is just a chart of where we get the CPU savings. So if I page fix, yes, then I save on the actual IOs. So for buffer pools with high IO rates, I save 1,000 instructions per fix and free, because if I'm going to bring a page into the buffer pool, I have to know there's a frame to catch it in real. Right? So I save 1,000 instructions per IO there in the buffer pool because I've page fixed it and I know it's mine. And then the other savings, right, is from the large, or from the TLB, translation look-aside buffer, meaning I don't have to map reduce down to figure out where my page is near as much, because with a 1 meg frame, there's 256, right, 4K frames in there, so it's easier for me to find it. So this is where, just kind of a summary of it. In summary of the buffer pool, you page fix. If you can't do everything, you can't page fix everything and back it all with LF area. If you got to do it incrementally, then you page fix buffers with high I/O. And when I say I/O, I mean read and write and prefetch, all of them. So whatever one has the highest I/O rate, that's the one I page fix first. If I want to back it with 1 meg frames or 2 gig frames, for instance, I do that based on get pages. It's frequency of reference. But page fixing, you get the most bang for the buck for the I/O. I think the last conference we talked about this, one of my customers asked about the work file, and then he'd been told that the work file buffer pools shouldn't be page fixed. That's probably your number one priority right there, is the work files, because they're always going to be going I/O, right? They're not going to be re-referenced by another application. So that's probably an easy one that would be at the top of the bubble sort. Okay, but if you overcommit them, it's bad. Now we'll talk about that. So large frames. So this is where you've got to go talk to your ZOS folks so they can reserve your large frame area, right? It's in the IASYS member of ParmLib. So outside your control, so you got to do the sales pitch. This is the pictorial version. My 1 meg frame, I'm going to reference, saves CPU in ZOS because he doesn't have to go search through 256 little frames. So then you think about a 2 gig frame, how many things he's avoiding having to go through for that. 2 gig frames sound like, well, it must be, 5,000 times better than this. Not really. In the performance, in our internal stuff at the lab, 2 gig frames didn't really pan out to show any difference. We weren't playing with that big of buffer pools. I've got a customer now that's using 2 gig frames that has 556 gig of buffer pool per DB2. They couldn't really measure a difference, but I can't argue it. I can't argue them against it.
Yeah, Robert Carroll told me that he had a customer that said did not even see it to start helping to at least a 20 gig buffer.
All right, so the comment was until you're over a 20 gig pool,
Yeah.
that you wouldn't see it. I can't find a customer who can show me the measurement that they ever saved, but if you're in the hundreds of gigs, I'm not going to argue against it, right? The downside is, like another customer, they used auto size on buffer pool and 2 gig frames, so I saw 180 gig swings in a 4-hour period of their buffer pool, and that's a lot of accordion effect on the ZOS, right? So large frame, this is our metrics of what we saw in the lab using our IRWW workload. That's the semantics of it, but this is nothing. This is page fixed. This is page fixed with 1 meg pageable frames for the control blocks. That takes a lot to explain, but we put this out in the maintenance stream in 10, so you've pretty much all got this. The pageable 1 meg frames for control blocks. And then this is page fix, pageable 1 meg frames for control blocks, and large frame area. The difference here, 4 to 5% total. So the big one really is page fixing, and then you get a little icing on top with large frames. But this is what we have out. I think this is in the version 10 performance manual. So more about 1 meg frames. Who gets the best bang for their buck? Well, DB2. I think Java can use it for their for their heap size, right, for garbage cleanup. But aside from that, we're using it. So you should size it based on DB2. You have to page fix it first until 11, and then you can specify frame size of 1 meg even without page fixing. That makes no sense to me at all because you probably won't be able to measure that very well as far as the CPU difference. Page fixing is the first one. And if you don't page fix it, you use 1 meg frames in there, and then you page the frame out behind the scenes, you've lost any savings you'd ever have out of it. The other thing we do is in version 11, the 31-bit storage that we use below the bar, that's backed by 1 meg frames, and also outbuff. So the output buffer for your log records. To allocate it, I said it's in the ParmLib member, LF area, 2 gig. It's either a percentage or a specific number. Be careful with the percentages, because you set a percentage, you upgrade the box, or you add storage, and suddenly that is already, right, contributed to this or volunteered to it without your knowing. So this is my calculation for how to size LF area. Based on DB2, 1.04, because the control blocks, of all the VP size, plus a little swag, plus outbuff, and then whatever is 31-bit low private. So that together is the max we're going to use. If you undersize it, you've left a little bit of savings on the table. If you oversize it and you run short on real storage, you're in deep duty, right? Because we don't like to break this down. We don't like to break down the storage. And ZOS will continue to try to coalesce those frames to go back up to the number you specified in IASYS, right? So too big is definitely not good. If you've sized it conservatively, we'll give you an IRA message that says, hey, we used all of LF area. So that means the next time you IPL, you can go, oh, okay, well, I'll add some, right, to increase it. So I said IPL. That's the only time you can change your PimeLab member for LF area sizing is at IPL. So if you make a mistake and it's too big, you're going to have to beg and plead for an outage to take it back down. So decomposing and coalescing is expensive. You'll burn way more CPU here than you could ever save by implementing this in the wrong way. So how do I know if I've oversized it? Well, display virtstore command LF area. So in this, you'll see this list of output. What I'm looking for is LF area allocated 4K. Allocated 1 meg is what you wanted. Large frame area is 1 meg or 2 gig. LF area allocated 4K means I had the large frame and then I broke it down. I decomposed those into 4K. This customer implemented it and said, I put about 5 gig, 4.8 gig of LF area, and DB2 is not using it for the buffer pools because I did a display command here on the buffer pool, and I can see that frame size preferred is 1 meg, and he's using only 4K. Why is this? So I asked for the output for this report, and this is his output. He's not here, but Cliff knows who he is. So at one point, 4.7 gig was allocated 4 meg. So we broke everything that he defined as large frame. We broke every single piece down into 4K. So if you could measure that, it'd be awesome to see what the uncaptured time in ZOS was for us breaking that down behind the scenes. So if these are non-zero, you have LF area allocated too large, so you either need to drop that or increase how much you have allocated on the LPAR. That's the only two answers for that. And then once again, we've added, for 2 gigs as well. Okay, so pageable 1 meg frames. I mentioned we put this back through the maintenance stream in version 10. There was a misnomer when it came out that you had to have Flash Express on the box to take advantage of it. That wasn't true. You just had to have a Z196 or up, right? So you already have this on everybody in here already has this. You're getting this benefit. I wish more customers measured it and noticed it so we could make a big deal about it, but it's on there. You can prove it's on there because if you go into the paging report, you'll see how many fixed frames and how many pageable 1 meg frames. And in this case, total available are 0 because they're all in use, and that means your buffer pool, you have enough buffer pool control blocks that used 1/8 of the storage on the LPAR. So that's great because these are the most highly referenced of anything in the buffer pool, and hence they get the best benefit from being backed by a 1 meg frame. So you can look in here and see they're being used. In this case where there's none available, we've used them all, they will overflow into LF area. And then you'll see LF area allocated pageable 1 meg. This guy has 130 meg of control blocks back there, and that's perfectly fine, working as designed. So if you oversize LF area a little bit, give some padding to grow on, then you might be able to back some of the control blocks there. Okay, Flash Express. So a couple of people have Flash Express. When this came out in the ZOS world, some of the hardware reps were gung-ho about it. Like I said, it's kind of like a thumb drive in the KEK. I heard somebody on the phone say, well, now you can supersize your buffer pools and they'll just page to Flash. No, don't do that. If you page to anything, it's bad. I don't care what it is, Flash or auxiliary. But this is my little number sheet that out of the red paper there. So access to real memory, depending on lots of things, and this isn't a Z14 reference, but about 1,000 machine cycles. 10x, well, actually, 100x more for Flash, and then 100x more for aux. So it's better than going to auxiliary, but it's 100 times worse than going to memory, so put everything in central storage. One of our teammates from level 2, who's even more cynical than I am, calls this an insurance policy, right? So what we've done is Flash Express is your plexiglass windshield in case you get into a head-on collision, right? So at least you won't get cut on the way out. So that's what this is. Not a substitute for real. It is great if you have critical paging on in ZOS, which means you have PPRC Metro Mirror and Hyperswap. If you have Hyperswap capability in your shop, you've got critical paging on, and in which case, a lot of stuff in DB2 is fixed that doesn't need to be, and this is good to have as a backup. It's also in case, for instance, you took an SVC dump during the prime online period of the day. You didn't intend to, something bad happened, and in that case, the dump would page to Flash and would be done quicker than it was out to aux. We still don't want that to happen, but it's better. Actually, the red paper they did when Flash Express came out talks about that. It's a 5x reduction in the dump time it took, and a 3x reduction in the CPU they used. The downside is when you're talking about a dump happening in the LPAR, you need it to happen in seconds. If you cut it down from 20 minutes to 5 minutes, you haven't really saved yourself, right? Our favorite horror story about the dump size was a European bank, and they took a dump, and it took something like 25 minutes. They came out with a partial dump, so we couldn't give them an answer, and we needed a repeat. Well, that 25 minutes occurred on one LPAR because sympathy sickness around the group, because when it went non-dispatchable for a couple seconds, it held page P-locks, it held all kinds of stuff that you don't want to in a data sharing group. So they paused, and their version of the SEC noticed. So their high poobah came to their bank and said, we noticed that, don't do that again. Well, then 2 weeks later, we got a reoccurrence. Yay, level 2 got a reoccurrence, so we could try to troubleshoot it. They didn't add as much storage as we told them. They added like 1 gig. We said they needed 6. They added 1 gig. Now the dump only took 10 minutes. And then their version of the SEC said, if you do that again, I'm going to revoke your banking license. Because what happens is when that occurred, all the money could come into the bank and none of it could leave. Good for them, not good for the country, right? And this is the largest bank in that country. So we came back and did some more math, and they listened to us this time. And the CIO at that point said, you can have as much storage as you want. You just name the number, right? And we'll put it on the box. No problem. So they added, like I said, another like 6 gig. It dumped again the next week because that was still partial. Oh, painful. So still no answer. So they dumped it again on the 3rd week. It took 10 seconds, and nobody noticed. Only the sysprog found out that they had a dump in SVC. So moral of the story, have enough central storage for that.
And listen to you.
Well, yeah, it makes for a good story, though. If everybody was perfect, then this would be the boringest presentation ever, right? So summary, don't be short. You are burning CPU. So finally, we have some number to go along with that. Go back, if you're looking at LF area, I said do a little math, understand which ones, how you're segregating that work, and how it's going to affect other things going on in the system. And here's some references. So, any questions? I was waiting to hear a can pop in the background or something. But anyway, so thank you guys for coming out. Felt your evaluation. Appreciate it. And if you have any questions, we can talk about it downstairs. Thanks a lot. Page fixing? 8%. 8%. We got that in the IRWW workload, and we also got that number from a customer. So they had 70 or 90 gig buffer pool. In page fix 70 gig. It saved him 25% of the DBM1 address space prefix, and it saved him exactly 8% in the total class